Hello everybody. So we're going to continue with our vector addition skills today. We've already looked at how to represent vectors mathematically, how to represent them graphically. We've even learned how to add vector arrows graphically. We always draw them tip to tail. The resultant always goes tail to tail, tip to tip between the free ends. Okay? We've also looked at collinear vectors. In fact, we did 4 examples using collinear vector addition. Okay? Today, we're going to step it up a bit. All right? Today, we're going to look at perpendicular vectors. Whoops. There we go. Now you can see. Perpendicular vectors. All right, now these are vectors that are not parallel, but obviously perpendicular to each other. That means they're at 90 degrees to each other. Now, the math process we're going to use is not going to be the same as it was for the collinear vectors. Those we could add up, or if they pointed opposite directions, you add the negative or subtract. When they're perpendicular, we're going to end up using the Pythagorean theorem to find the magnitude, and we're going to be using some right triangle trig to find the direction of the resultant. Now, this is why you have already watched the 2 videos that show you how to use right triangle trig and what we'll be doing with it, and your 2 coordinate systems, the Cartesian coordinate system and the cardinal coordinate system. Couldn't think of it for a moment. The cardinal coordinate system and how we measure the angles relative to the horizontal on those, how we state the direction of a vector. All right, so let's just start by actually doing some. Please remember, my computer will not put the little symbols on top of vectors and axial directions, so we kind of need to do that ourselves. All right. Okay, now I'm going to blow this up a little bit so that we can see this side a little better. We're going to focus on this side for a little bit. We have 2 vectors that we're going to add, and if it's okay with you guys, we'll stick to pure math for right now. We've got 6 units, or if you consider a unit to be a square, 6 squares in the positive x direction and 6 in the positive y direction. We want to draw them tip to tail. Now, I'm going to give you one of my most secret little tricks that I've learned from years and years of experience. When you are drawing the vectors tip to tail, the smart thing to do is to draw the horizontal vector first. Doesn't matter if it's a displacement and you first went vertical and then horizontal. Remember that property in algebra says we can add them either way, we'll still get the same answer. So we're going to draw the horizontal one first, and from its tip, we'll put the tail of the vertical one and draw it up or down. Understand? Horizontal first, then vertical. I'll explain why that's going to save you so much agony later. Okay? We'll see in a little bit why it's a lot easier to do it that way. So I'm going to make a start position, and I'm going to go with the horizontal vector. I'm going to go 1, 2, 3, 4, 5, 6. There we go. So that's vector A. And I'm going to use green for the other one. So now we want to go 6 up. 1, 2, 3, 4, 5, 6. For some reason, my squares are a little squished, so the vertical length doesn't appear to be as big as the horizontal, but oh well, we'll overlook it. So there's our 2 vectors, and here are the free ends. They're still tip to tail, and now the resultant drawn between the free ends goes from start to end, from tail to tip. So it's tail to tail, tip to tip. Over and up. Always start with a horizontal, put the tail of the vertical on its tip, and then either go up or down depending on what it says for the vertical vector. So here's our resultant. Now, Mathematically, we can easily determine the direction of the resultant. All we have to do is use the Pythagorean theorem. So here's how I'm going to write it out. I'm going to do it like this. I'm not going to say r squared equals a squared plus b squared, because then I would have to write it a second time showing that I'm square rooting both sides. So why not just write it like that? Okay? Saves us a step. Now, to get the answer, all we have to do is say the square root of 6 squared plus 6 squared. And if you stick that in your calculator, you're going to get a value. Let me see what it is. There we go. You're going to get a value of about 8.5 if we round a little bit. Okay, so this is the magnitude of the answer, of the resultant. Now, real quickly, I want you guys to do the same thing on this side. We'll talk about directions in a minute. Let's just get down to diagramming and finding the magnitude of the resultant first. All right? So you just go ahead and try this one. Notice you've got 4 squares in the positive x direction and 7 squares in the positive y direction. You go ahead and try that one for a moment, and let's see if it, and do both the diagram and the math, see what you come up with, okay? And boom, look at that. Okay, my diagram looks like this, and I got 8.1 for the magnitude of the resultant. Now, if you actually wanted to measure the number of squares, like count them, obviously on a diagonal, you can't just say 1, 2, 3, 4, 5 squares. You'd have to cut out a strip of squares and lay it alongside the resultant and count them from that. You couldn't do it like we do here, just 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6, 7, because it is on a diagonal. But since it is on a diagonal, we'll forgo cutting strips to measure the length against the strip. We're just going to use the math. Handy dandy, that math. All right, now, so here we are. We've talked about how to determine the magnitude of the resultant when you're adding 2 perpendicular vectors. But that's only half the answer. All vector answers also have direction. But what is it on these? Well, I want you to look at each resultant. Are they in the x direction? No, because the x direction is directly to the right. This isn't directly to the right, it's to the right and up. Is it in the positive y direction? No, because vector B points directly up in the positive y direction. This doesn't. All right, so it's somewhere between to the right, or positive x, and straight up positive y. It's somewhere in between those two. But how far? That's where the right triangle trig comes in. When we have a resultant at an angle to the horizontal, what we want to do is we want to see how many degrees of arc are there between the horizontal and the resultant. That's how we're going to find the direction. And of course, how you reference it is very important. Number 1, we always measure the angle next to the horizontal. We never measure the angle next to the vertical. That's not standard convention in science. Okay? This is why I wanted you to always draw the horizontal vector first. Let me show you what I'm talking about. Sometimes, and it's not necessarily wrong to do this, it's just a little more convoluted. Sometimes people will do the vertical one first. They'll go up and then they'll go over, which is not necessarily wrong. You're going to get the exact same resultant. All right? It'd just be this half of the rectangle made by the vectors, okay? But here's the catch. When they do it this way, they want to measure this angle. And that's a no-no, because that's the one next to the vertical, and we don't reference from the vertical. We reference from the horizontal. So if you do, by accident, go up and then over, just measure the angle that's next to the horizontal vector. It'll be the same thing as the one down here, won't it? Because two parallel lines cut by a diagonal, opposite interior angles are congruent. So this angle is the exact same size as that angle, okay? But it does make your life a lot easier if you will simply make it a habit to go over and up or down, okay? Over first, and then put the tail of the vertical one on the tip of the horizontal one. That way, your angle is right there where you want it, okay? Next to the horizontal, without thinking about that one, all right? It will save you a lot of agony if you think ahead. All right, so just for a brief minute, I want to talk about how we're going to reference these angles for the actual direction, not just a measure of arc, but how do we state what that direction of arc is for us. So we've only found the magnitudes right now, and that's fine. So we need to know the direction, and we're going to use degrees of arc designated with the letter theta. So we want to know, how do we use a reference coordinate system to state what that angle theta is in reference to our coordinate systems? And there are two coordinate systems, and how we use them is very important. And the very first rule for using a reference coordinate system is that we always place the origin of the reference coordinate system on the tail of the resultant. Always. All right, so let me do that. Let's come up here. Remember our start position? Well, it ends up on the tail of the resultant, doesn't it? Because we always say tail to tail, tip to tip, tail to tail, tip to tip. So our start position is already there. We're just going to make it the origin. So I'm going to dot in a little y-axis and a little x-axis. Do we have to have three huge other quadrants when we know it's going to be in the first one? No. Focus on the quadrant you're concerned with. Don't extend your axes out and waste a lot of paper. That's just ridiculous, okay? Over here, we're going to put our origin here, where our start is, and we're going to dot in a little y-axis, dot in a little x-axis, okay? Now, let's talk about what we do next. It says, check the problem to see which type of coordinate system the given information indicates. Okay, well look at the given information. It says x hat, y hat for both of these. No north, south, east, west. So if there's no north, south, east, or west, you're certainly not using the cardinal system. You're using the Cartesian system. Okay, so we need to label our axes accordingly. All right, so I'm going to. We have positive x hat here, positive y hat here. And if you want to label the negative ones, that's all right too, but it's not necessary since we're focused on the first quadrant here. Now, if your vector does lie in, y, not x. If your vector does lie in one of the other quadrants, obviously, then you would want to label the negative ones if you're using them. Okay, so we've done that. All right, so we've found out what coordinate system we have. We've labeled our axes. Now we're going to use the reference coordinate system with our right triangle to find the direction. All right, so in both these cases, we happen to be in the first quadrant. And we learned in our reference 12 yesterday in that video that we're going to be measuring from the x-axis, which is 0 degrees, around towards the y-axis. We always start from the horizontal and measure around towards the vertical, okay? So these are the angles we want, and we're going to say that they are that many degrees above the positive x-axis, okay? But we need to find them. how do we find those measures of arc? Okay, well, let's show you. This is what we learned in our 11 yesterday, our right triangle trig. We know that we were given vector A, which was 6, and vector B, which was 6, and we also now know the resultant. But I don't like to use the resultant to find the angle in case I made a boo-boo right there, because it does happen quite a bit. So I'm going to use these two legs, A and B. And whenever you use the two legs, the only trig function you can use is the tangent function. Now, we know that the tangent of the angle, according to Pythagoras, the tangent of the angle is the leg opposite the angle divided by the adjacent, op over adj, right? In this case, the leg opposite is B, and that's 6, okay? The leg adjacent is A, and that's 6. So we get the tangent of the angle is 1. Fine, but guys, here's a little problem. We want the angle, not the tangent of the angle. We know the tangent of the angle is 1, but we want the angle. So what do? We have to get rid of the tan. How do we do it? We take the inverse tangent of both sides. If we take the inverse tangent of tangent theta, the tangent and inverse tangent cancel, and you're left with theta. On the other side, you take the inverse tangent of 1, and you're going to get 45 degrees. Okay? That's how you do it. Now, I have found over the years that instead of writing this out all the time and then doing the inverse tangent, it is a lot easier to do this. Okay? Let me show you on this one a little shortcut. If you already know you're going to have to take the inverse tangent of both sides, then why not write it like this? Why waste a lot of time on something you already know? And if you're always referencing from the horizontal, then the horizontal will always be the adjacent leg, and the vertical will always be the opposite leg. So we can say the vertical or y vector over the horizontal or x vector. So why not just write that every time? Why mess with all that? So, okay. On this one, we're going to say the inverse tangent. The y vector was 7. The x vector was 4. And now, when you stick that in, and in your calculator with the inverse tangent, remember to do the inverse tangent, you just hit second tan. That usually does it on most calculators. Second function tan, and it'll give you the inverse. And I believe you get about 60.3 degrees for that one. All right, so now we've got the magnitude and the angle. Let's write the answer appropriately now, both parts together. So watch this. Here the resultant is 45. Boy, I tell you, I'm doing really good today. Okay, let's try that again. Has a magnitude of 8.5 units, or squares in this case. If it was a physics measurement, we'd put the units there. I just use this at symbol, 45 degrees above the positive, positive x-axis. There we go. That's the answer. Okay? So now, how would we write this one? Simple. First, we say R equals, and we start with the magnitude, 8.1 units at a direction of 60.3 degrees above the positive x-axis. And if you watched the videos yesterday on how to use your two coordinate systems, you know that if they're in the other quadrants, you could say above or below the negative x-axis. You could also say below the positive x-axis if it's in the fourth quadrant, okay? And also for your cardinal system, you would say north or south of the east axis. You just have east here and north here, so you'd go north or south of the east axis. Or if it's in the second or third quadrant, you'd say north or south of the west axis. So that makes it easy, okay? All right, so not too bad, is it? All right, we're going to be practicing doing some of these. The pattern is still the same. You do your diagram, make a start point, draw your horizontal vector first, whichever way it points. Then from the tip of it, you go up or down. Then you draw your resultant tail to tail, tip to tip, and put your origin of your axis right there on the tail of the resultant at your start point. All right, then mark your angle for your direction, the one next to the horizontal vector, always. Then you can use your math, Pythagorean theorem to get the magnitude, inverse tangent of opposite over adjacent or vertical over horizontal to get the angle. Then you put the two pieces together, stating if you're above or below whichever axis you're closest to. Okay? All right. I'll let you have at it now. Thanks, guys.